Okay, so here we're going to look at regression. And the idea behind regression is we're going to see how two variables may be correlated with each other. So for example, exam scores may be positively correlated with the time spent studying. So you would expect the more time spent studying, the higher the exam score may be. Fuel efficiency in miles per gallon may be negatively correlated with the weight of a vehicle. So you would probably expect that the heavier a vehicle is, the smaller or less miles per gallon or fuel efficiency that vehicle would get. So when given a set of data of the form XY, we may create a scatter plot. The following is a scatter plot of weight and mileage in miles per gallon. Okay, so that's MPG instead of MPH. Okay, that was a mistake. Okay, so in general what we can see is that it appears as the weight increases, so as the weight gets larger, so you go from 2 to 3 to 4 to 5,000, it appears the mileage in miles per gallon, it appears decreases. Okay, so the general trend looks like it's downward. Now a question arises as to how strong the correlation is between the weight and the mileage. Okay, and the idea is we want to be able to predict if we were given the weight of a car, could we find the expected or predicted mileage that that car would get, and vice versa. If we were given a mileage, could we predict the weight of the car? Okay, so the concept of regression is to draw a curve, okay, what may be linear, quadratic, exponential, a sine curve, etc., that passes through the data points. However, much of the time, the data points will not lie exactly on one of these curves. However, the data may be close to one of these curves. Okay, so that's the essence of a model, is that we want to draw a line that is close to the data points. Okay, so on the next page, here we're going to focus on a linear regression model. Okay, so the graph below shows our goal when drawing what we call a line of best fit or a least squares regression model. Okay, we have a set of points x, y. Variable x is called the explanatory variable, and variable y is called the response variable. Okay, so in our example from before, the weight would be the explanatory variable, and the miles per gallon will be the response variable. Okay, and our goal when looking at a linear regression model, or the line of best fit, the line of best fit here is drawn through this data set. Notice that that line does not go through any of the points. Okay, so we have a point here, point here, point here, and so on. Okay, none of those points actually lie on the line. However, this line that is drawn is the line of best fit or the least squares regression model. To draw that line, what we do is we look at something called a residual. A residual is the difference between the observed data value on the scatter plot and the predicted value on the line of best fit. Okay, so the residual, if we look at here, the distance from here to here, or that residual, if you take the actual value of maybe 17, and then the predicted value maybe around 14, so that residual would be 3. From here, from this actual value to the predicted value, well, from if you do 5, take away maybe 15, that residual would be negative 10. And then the next residual may be a distance of 2, or positive 2 when you take this value, like 20 minus maybe 18. Okay, and you could do that for each of these. Okay, what the line of best fit is, or the least squares regression line, it's the line that minimizes the sum of the squares of the residuals. Okay, so the idea is we want the distance between our line of best fit and the data points. Okay, we want that to be as small as possible. Now the issue is, if I were to take a line, and just suppose I drew a line, if I said my linear model went through the first 2 points, so the side of my pen, pretend that was a linear model, well, that's a terrible linear model, because even though it goes through the first 2 points, it's not even close to the rest of the data set. Okay, and you can play along forever if you want here, or for several different values. Suppose I drew it through maybe this point and this point. So if I draw a line through those 2 points, okay, so if we were to take that line, okay, so take the side of my pen, well, that's a lot better than the first one, but that line is above all the data points. So obviously the distance from the line to the points is not minimized. Okay, so the idea is which line is the best? Well, it just so happens the line that's drawn there is the best. Okay, because that is the line that will minimize the sum of the squares of the residuals. Now the reason we have the squares of the residuals, if you remember back to when we did standard deviation, S equals the square root of the sum. That's a terrible sum symbol. That's a sum of x minus x bar squared divided by n minus 1. Well, that x minus x bar, that was the distance between a data value and the mean. We squared it to make it a positive value. Okay, so that distance was positive. Okay, so that was our goal. That was we want to represent distance as a positive. Same idea here. If we take the squares of these residuals, when you square 3, you get positive 9. Square negative 10, you get positive 100, and so on. So then you can look at them as a distance. Okay, so same idea there. Okay, so this is the line that minimizes the sum of the squares of the residuals, and that line, again, is called the line of best fit, or the least squares regression line or model. Okay, so going back to our example of the weight of cars in miles per gallon. Now, I didn't want to use every single point. What I did was I took several points from this scatter plot, and rather than have us put like 50 points, all these points in the calculator, okay, rather than do that, I just chose several to use, for, and I put those in this table. Okay, so we have weight in miles per gallon. And the good news is we can use technology to find the equation of the least squares regression line. We enter the explanatory variable, okay, the x values, or the weight in this case, in list 1, and the response variable, or y, the miles per gallon, in list 2. Okay, so you should have used your calculator several times in a similar manner. You press stat and then edit. That'll get you to your list. Okay, and I already have the values in the list. I forgot I eliminated the last one, so let me put the last one in here. Okay, and then we do stat, calculate the lin reg ax plus b on list 1, list 2. Okay, so we go to stat, calculate lin reg on second 1, comma second 2. Okay, because that's where we put our values in list 1 and list 2. Okay, and it gives us our y equals ax plus b, and a is negative 0.00656 and b 39.9116. I notice it gives us an r squared and an r value. Okay, now I'll explain this on the next page, that if you don't get the r and r squared value, okay, and this is explained on the next page, but what you do is you do second 0. Okay, so you see how it says catalog above 0? It may be hard to see on the screen here. But if you do second 0, and then you can scroll down to diagnostics on. Now a shortcut to get there, you see how it says D above that, above the x to the negative 1? And then you can, that'll take us to the D's, and then diagnostic on. Press enter, and it'll say done. And then you do the stat calculate again, the lin reg, ax plus b. Okay, and then your r squared and r will show up. Okay, so the values on our calculator, they give us the slope and the y-intercept of our linear regression model. Okay, so there should be nothing too difficult here because we're just looking at a linear equation. Okay, now when we look at the values, okay, one important thing is here to recognize that we're using our equation to predict the mileage given the weight of a vehicle. So what we do is we use y hat as the predicted value given x. Now, if you remember back in the confidence intervals or back in the binomial, we have p hat. Okay, so remember we use p hat. That was x over n. Okay, the number of successes divided by the sample size. And that was our predicted value for the population percentage. Okay, p hat is the predicted value for p. So y hat is the predicted value for y. Okay, so we write our slope times x plus the y-intercept. Okay, so that's y equals ax plus b. Okay, and when we look at explaining the meaning, okay, the slope is the coefficient of x, and this is a little awkward, but if you remember slope, rise over run, because you remember that idea of rise over run. Well, rise in our example, again, this isn't our exact scatter plot, but it's the same idea. That's the mileage in miles per gallon, and then the run is going to be in weight, in pounds. So when we see a slope of negative 0.00656, something was decreasing. Well, what's decreasing? The mileage. Okay, the y values are decreasing. Okay, so the mileage decreases by 0.00656 miles per gallon per the run. Well, the run is weight in pounds. Okay, so per pound. So the mileage decreases by 0.00656 miles per gallon per pound. Okay, and that's an awkward rate of change there because it's a rate of change within a rate of change. So it is a little awkward. Another way to think about it would be if you were to multiply that by 1,000. So move the decimal point 3 places right. It'd be negative 6.56 miles per gallon. So what that would mean is the mileage decreases by 6.56 miles per gallon per every 1,000 pound increase in weight. So if the weight goes up by 1,000 pounds, you would expect the mileage to decrease by 6.56 miles per gallon. Okay, so that might make more sense in our heads when we think about it. Okay, and then part C, the y-intercept. Well, that's the number all by itself there, the b value. So 0, 39.91, which means if x is 0, so if the weight of a car is 0, we would expect it or predict it to get 39.91 miles per gallon. Now we know that we're not going to have a car that weighs 0 pounds. So in the context of this question, that would make no sense. But that's how you would interpret that answer. Okay, and then part D, if a car weighed 2,200 pounds or 3,500 pounds, what would the predicted miles per gallon be? Okay, well, I'm just going to put it up there quickly because this should be a pretty basic question for us. If I give you a weight, that's giving you an x value, so put those values in for x. So the 2,200 pound car, we would expect to get 25.478 miles per gallon. And a car weighing 3,500 pounds, we'd expect to get 16.95 miles per gallon. Okay, and then moving on to the next part. Okay, part E. What would we expect the weight of a car to be if the mileage is 27 miles per gallon? Well, now that's given us a y hat value, a predicted mileage of 27 mpgs. So we solve that equation. Okay, so subtract 39.91 and then divide by the negative 0.00656. And that gives us 1,968 pounds. Okay, and then if we looking at the R and R squared values. Okay, so now we'll explain the strength of correlations. Okay, so I give you a summary here, and this is not our example. Okay, this is just a summary of correlation in general. Okay, so we can have a positive correlation, positive, 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 or we could have a negative correlation, and we could also have no correlation. And the basic idea behind a positive correlation is basically just saying that the line that you draw, the line of best fit, would have a positive slope. So as x increases, y increases. So when we look at a perfect positive correlation, okay, that has a correlation coefficient, an R value, of 1. So if we were to draw a line, that line would pass exactly through those points. Okay, so that would be a perfect positive correlation. Okay, perfect because it's going through all the points. Positive because it's a positive slope. A high correlation, well, if I drew a line of best fit there, it may look something like this. And we can see the general trend is upward. And notice that the points are clustered pretty close to that line. Okay, so that's a high positive correlation. The R value will be about 0.8. Okay, 0.9, they'd be even a little bit closer to the line, and so on. A low positive correlation means if I draw that line of best fit, the lines are a little more scattered around that line than they were for a higher correlation. Okay, but we can still see the general trend is upward. Okay, for a negative correlation, I'm going to skip the no correlation just for a minute. Negative correlation, okay, again, the perfect positive, the perfect negative correlation means we have a negative slope and the line passes through all the points, so that would be a perfect negative correlation. A high negative correlation, when we draw that line of best fit, the points are pretty close to clustered around that line, so negative 0.8. Those are just the opposite cases of these two here. And then a low negative correlation, if I draw a line like that, again, the general trend is downward, but those points are pretty scattered around that line. And then no correlation, if I were to draw a line here, well, those points are really scattered around the line, and it's not any better of a line than if I drew a line through like this. Okay, so the points are not any closer to the blue line than they are the red line. Okay, so that would be an example of no correlation. Okay, so the values of the scatter plot show the value of R and the linear correlation coefficient. Okay, that's the R value. And note that it's always between -1 and +1. The closer you get to 0, the less the correlation there is between the variables. And a perfect correlation is an R value of -1 or 1, which means that the model passes through every point on that scatter plot. Okay, so to get to a scatter plot on our calculator, okay, I'll give you the screenshots here. Okay, but it's pretty easy. Okay, on our calculator, if we do second y equals, it's stat plot, we want to turn the plot on. So plot 1, we're going to press enter, and then press enter again to turn it on. And the type, okay, there's a few different types. The first type there is the scatter plot, which is what we want. The other type, that's a connected graph. Then we have a frequency histogram. Then we have a couple box plots down here. Okay, those are box plots there. Okay, what we want is we want the first choice, so highlight that. And then arrow keys, we have L1 and L2. That's where we put our values in our list. And then the mark is just how it's going to show up on the screen. Okay, and then to get the actual picture of the scatter plot, we press zoom, and then option 9 is zoom stat. Well, we put our values in our stat menu under list 1 and list 2, so we'll zoom stat, and it draws our model. Now let me go backwards a second here. Okay, so when you do that, that'll show up. Okay, now if we want to graph the line of best fit, well, the line of best fit, if we go to y equals, we can enter that in to y equals. Now I have another one in there, but I want you to focus on y1 right now. Okay, that was the model that we got. Okay, and then if you press graph after you put that in, don't forget the x value, or the x variable. The x variable is xt theta n. Okay, so graph that, and there's our line of best fit. Okay, and we can see that those points, they follow a general downward trend. Okay, just like our scatter plot with about 50 points on it did. Okay, and then excuse me, we can look at the value of r and r squared. Can we just go to question 2 right away? Explain the meaning of r in the weight and miles per gallon of cars example. Well, the r value was negative 0.82, and we can see here that those points have a fairly strong negative linear correlation. Okay, so there's a fairly strong negative linear correlation between weight and mileage. Okay, so the key words there, strong negative linear correlation. R squared, okay, so part B, looking at r squared, well, the r squared value was 0.673. And on the top of the page, this is how you explain the r squared value. R squared tells us the proportion of the variation in y that's explained by the linear relationship between x and y. Now that sounds confusing, and it kind of is, but the r squared was 0.673. So about 67% of the variation in mileage, the y, can be explained by the linear relationship between the weight, x, and the mileage, y. Okay, so basically saying that when you look at the relationship between the mileage and weight of a car, the weight, it appears, has a high correlation with how the miles per gallon may change. Okay, other factors, maybe if that was an r squared value of 1, then we would say that 100% of the variation in mileage is explained by the weight. Okay, and that would mean that you would really not look at any other variable. But with only 67% explained by weight, other things that can affect mileage or that may be correlated with mileage are things like size of the tires on the car, things like the size of the engine. I don't mean the weight of the engine, but like the size of it. Like some engines will use more gas than others for more power. So there's several different variables that will be related to the mileage that a car gets. Okay, and then the very last question here, if we look at removing the point 2,000, 35, so the data value that a car weighed 2,000 pounds had mileage of 35. Okay, if I delete that point, and then if I look at the scatter plot again, so if I do zoom 9, okay, notice that the point that was much higher is removed. Okay, well now if I do stat and then calculate the lin reg again, now the slope is negative 0.0052, and then the y-intercept is 35.34. Okay, so the slope is a little less negative, and the y-intercept is about 4 less than it was before. Okay, and the r squared is 0.94, r is negative 0.97. So now we see there's a much stronger negative linear correlation than before, and much more you can attribute the variation in mileage. Okay, we can attribute almost 95% of that to the weight of the vehicle. So that point that was there previously that was much higher than the other data points was really influencing the relationship between the weight and the mileage. Okay, and if I go to my y equals, and I graph that new equation, okay, because the equation that was there before was when the other point was in there. Now, this line, okay, this line here is our new line. Okay, we see that it looks like it really is closer to all the points. Okay, the line here, it kind of veers off going higher. Okay, so it looks like we have a better model now, and that shows up in the correlation coefficient. Okay, so that's it for scatter plots and linear regression and correlation.